welcome back to the fifth lecture of bioelectrochemistry. So, in the last class I started with the galvanic cell and I gave you a classic example of zinc copper electrode and how the cell is formed. So, one of the challenging part of offering a MOOC lecture is that you do not have a classroom in front of you. So, that kinds of prevents you from getting bombarded with questions which are very genuine and which confuses the students all the time. And with these kind of electrochemical cells, it always remain for several students to figure out how the electron is flowing, how the ion is flowing. It's very interesting. While I was sharing this lecture with the TA of the course, Ms. Himanshi Jangir, she pointed out something very interesting. What she told me is that in our lecture, we haven't really highlighted how the electron flow and the ion migration or diffusion is happening. So, what I decided is that in this lecture, I will again revisit the galvanic cell, though this is the last lecture of this week. So, kindly do not get worried. I have another 15 lectures and I am moving slowly because once these basic fundamentals are clarified, then rest of the story will become much more easy. But if there is even one small doubt remains in the fundamentals, then you will always have problem all throughout and again you will have to revisit all the fundamentals. So, today we will revisit the galvanic cell again with a different form of electrodes. So, if you remember yesterday when we talked about the galvanic cell using copper and zinc electrode, we talked about, so there is a semi-permeable membrane and copper is deposited in its corresponding salt, zinc is deposited in its corresponding salt, and zinc is behaving as an anode where the oxidation is taking place. Zinc is losing its electron and becoming zinc ion, and that electron is flowing through the circuit to the copper electrode, so on and so forth. Today we will take two cases. In one case we will talk about, the first case what we will be talking about is a cell where there is a common electrode without having that semi-permeable membrane. And then we will take another situation where we will be having two different electrodes mixed together without having the semi-permeable membrane. And in the third case we will talk about what is the need of the semi-permeable membrane, or what we call as the salt bridge. I haven't introduced the salt bridge. So, this is what we will be covering today. So, let us start lecture 4 or lecture 5, sorry, lecture 5. So, let us again revisit the definition of the galvanic cell or the voltaic cell. Galvanic cell, this is also called voltaic cell, sometimes it is special case called Daniell cells. Okay. It uses spontaneous chemical reaction to generate electricity. A spontaneous chemical reactions to generate electricity. So, this is our basic fundamental definition. Okay. Based on this definition, there are few conditions to accomplish this. In order to accomplish this feat could be only accomplished when one reagent must be oxidized, must get oxidized, whereas the another one, the second reagent must get reduced. This is our basic fundamental. And the next most important thing what we will be dealing today, the two cannot be in contact. The two, which is this one and this one, cannot be in contact. Contact means I am talking about a physical contact with each other. They cannot be in contact, because if in that case the electrons would flow, if say for example, if they are in contact, let us assume a situation, if these are in contact, in that case the electrons would flow directly from reducing agent to the oxidizing agent. So, and we will talk about such a situation, directly from reducing agent to oxidizing agent. So, you have to prevent the physical direct contact, and how we achieve that. So, we will take two case studies which will tell you how that is happening. Okay. Instead, oxidizing and reducing agents are, so oxidizing agent and reducing agent are physically separated, they are physically separated from each other, and the electrons are forced to flow through an external circuit. So, essentially something like this, there is an external circuit where you are basically forcing the electron to flow through. Okay. So, you are keeping a physical barrier between them and they flow through the external circuit to go from one reactant to the another. Now, there are two terms which I have used and today I wish to highlight, which will come very handy in future when we talk about batteries, where you will find a lot of applications of this, or the fuel cell. I am just giving a small hint and then I will again carry over from here. So, when you talk about a battery, essentially it is a galvanic cell that consume the reactants to generate electricity. Both of them are galvanic cells, by the way. Both these are examples of galvanic cells, but there is one small difference in terms of the amount of substrate which are present. So, when you talk about a battery, the case of a battery, so that is the situation when we talk about a static compartment filled with reactant. It is an static compartment filled with reactants. On the contrary, if we talk about a fuel cell, in case of fuel cell, the fresh reactant flow past the electrode. So, you are continuously supplying fresh reactants flows past the electrode and products are continuously flushed from the cells, are flushed from the cell. So, keep this in mind, these are two very important applications. So, in other words, when we talk about a fuel cell, essentially what we are talking about is you are continuously, there is an input of the reactants. So, there is an electrode, there is an input of the reactants, and the product which is coming out is getting flushed out. Whereas, in the case of a battery, it is a static chamber where the reactions are continuously happening without much shift. Okay. So, keep that in mind, because these galvanic cells will come very handy, and that is one of the very basic reason why I am spending more than stipulated time for you people to understand this. If you understand this, understanding battery, understanding fuel cell, biofuel cells, everything will become much more easy. You will be able to break up the system in terms of anode, cathode, electrolytes, reactants, products and everything. Okay. So, let us carry over. So, now let us draw another. So, we talked about the copper and the zinc in the previous class. So, today we will talk about a different kind of electrode where it will be a cadmium and AgCl. So, to start off with, so let us draw a galvanic cell where you have an electrode which is cadmium electrode CD, okay, and you have a AgCl electrode which is Ag, and here you have, so here you are having the electrolyte, okay, and this is kind of coated with AgCl. So, this is an AgCl, silver chloride electrode. Okay. So, silver chloride electrode, this is a solid electrode here, cadmium, this is also a solid electrode here, and this is connected to a voltmeter or potentiometer. To measuring the voltage across it. Okay. And cadmium in this case is the one which is, so what is the electrolyte? Electrolyte is cadmium chloride. So, you are seeing I have not put any separation out here, and for your interest this is around this much molar. So, which has been standardized over a period of time, and in this case your cadmium is the anode, and as you remember, anode is the place where the oxidation is happening. So, in other words, at the anode what will happen? Cadmium 2 plus will go to the aqueous solution. So, in that case there will be an electron which will be generated, which will be traveling in this circuit like this. Okay. Whereas, on the AgCl solid electrode, which is in this case is an cathode, where essentially a reduction is happening. In this case, the chloride will come out into the solution, Cl minus in the aqueous solution, the chloride will come out, and here you are having the AgCl solid electrode. So, this electron which will be coming, so in that case this polarity will be positive, here it will be negative, and this is that external connection, the where, and the electron is coming and reducing the Ag plus, which is generated because silver is leaving behind and coming into the solution. Okay. So, in other words, the chloride is coming into the solution, leaving behind the silver with an additional positive charge, which is being nullified by the electron traveling from the cadmium side. Okay. So, let us talk about it. So, this is basically a simple galvanic cell, potential that measuring the voltage, okay, and it has a positive and negative terminal, and when the electron flows into the negative terminal as the illustration, the voltage is positive. Okay. So, keep that in mind when electron is flowing or electron flows into the negative terminal, as in this illustration, the voltage is positive. Okay. So, there is a positive voltage which is getting. So, this is an axiom by which we define these kind of situation. Okay. Now, having shown this, now we will talk about what are the reactions which has happened. That is the important part for us, that is the what we have to take into consideration. So, there are two reactions which are happening, and mind it, there is no semi permeable membrane here. So, there is a reduction reaction where 2 AgCl, which is your solid, and you have to mention always which is solid, which is aqueous, plus 2 electrons which are traveling from cadmium after cadmium getting oxidized, making it 2 Ag, which is solid, plus 2 Cl minus, which is in aqueous. Now, tellate, here is that, let us start with this term. Here you are having that chloride aqueous 2 Ag. So, this is your AgCl electrode. Okay. On the AgCl electrode, you are having Ag solid. Okay. Second term, talking about the two electrons which are traveling. So, here you are having those electrons which are traveling from cadmium. So, AgCl, so chloride is getting lost into the aqueous solution, and 2Ag which is left with the positive charge is getting reduced out here to make Ag metal. So, there is a deposition of Ag metal and you are continuously losing the chloride from it. Now, what is the oxidation reaction which is happening? The oxidation reaction, you are having the cadmium which is the solid, you see that solid cadmium out here, and the solid cadmium is getting oxidized, becoming Cd2 plus in the aqueous system. So, you see this is that aqueous solution and it is losing those two electrons. Those two electrons are shown here. These are the electrons which are traveling. Now, if you add up this reaction out here, what you are going to get in this redox reaction, you have net reaction, you have cadmium which is solid plus 2 AgCl which is also solid, making. So, there is a migration of cadmium 2 plus or cadmium ion into the aqueous solvent plus 2 Ag which is on the solid deposition and 2 Cl which is the aqueous. And you remember we use cadmium chloride as the electrolyte out here. So, this is what is happening in this situation. So, if we summarize it out here, so the oxidation of cadmium metal to Cd, so basically the oxidation of cadmium metal to Cd2 plus in aqueous solution provides electrons which flows through outer circuit, okay, to the Ag electrode or silver electrode, and on the silver electrode at the surface of the Ag surface, at silver surface which is basically the AgCl. So, keep in mind it is not the pure Ag, it is a AgCl. From AgCl is reduced to Ag solid, okay, and chloride from, keep in mind this is the chloride from AgCl goes into solution. So, keep this all these things in mind, and here is the important part. You might be wondering where I was talking about all this free energy. So, the free energy change for this net reaction, the net reaction what is being shown here out here, for this whole reaction the free energy change which is happening is minus 150 kilojoule per mole, okay, of cadmium. So, this is the free energy change, or delta G is equal to minus 150 kilojoule per mole of cadmium provides the driving force for this reaction to occur, okay, driving force for this reaction to occur. Now, in other words, this is the driving force that pushes the electron into the circuit. This is the driving force pushing the electron into the circuit. So, keep that in mind. So, this is where the electron is coming. Now, if you remember the formula what I taught you earlier, could you calculate the voltage? If you remember, the formula was delta G is equal to minus N F E. where E was the voltage. So, what we have to figure out is the E, right. So, E is your unknown parameter. Now, if you put it like this, so E is equal to minus delta G upon Nf. Now, if I plug in the values, now you will see what is the voltage. So, what we are essentially trying to find out, what is the voltage value you are going to see. Okay. So, you have other parameters. So, you know this reaction will happen at minus 150 kilojoule per mole of cadmium is getting consumed. Okay. So, if this is the situation, then the value of E will be minus 150 into 10 to the power 3 joules, so that was in kilojoules. So, I am converting that into joules, divided by 2 moles, okay, 2 moles multiplied by F, which is Nf, Faraday's constant, which is 649 multiplied by 10 to the power 4 coulomb per mole. Now, if you calculate this value, this will come as, so there is a minus already here, and this equation is also comes with a minus. So, this minus cancelled. So, this is what it is. And oh, by the way, I haven't mentioned that. So, basically what you are calculating is the voltage produced by the chemical reaction. Okay. So, now what you are having is that you might be wondering why I put 2 moles here. Now, if you recollect the reaction, what happened in the reaction of the cadmium, so that will clarify why I put 2 moles there, because if you see the reaction, so if you see this generate 2 electrons. Okay. So, we assume those 2 electrons are basically 2 moles. You can always say 2 electrons or 2 moles of electron, because you cannot really calculate the number of electrons there. So, 2 moles of electron, that is why I put it as a 2 moles. Okay. So, that this value, the 2 moles what you see should not confuse you, it is because in that reaction. So, you should always remember the reaction, the first reaction what you saw was CD solid. So, cadmium becoming 2 plus aqueous plus 2 electron. So, this is the reaction which is governing this whole flow of electron. So, 2 moles there. So, minus becomes plus, and as I told you, so 150 multiplied by 10 to the power 3, and if you do this whole calculation all by yourself, what you will be generating is plus 0.777 volt. So, this is a spontaneous chemical reaction, negative delta G produces a positive voltage. Okay. So, negative delta G producing a positive voltage, and this is an spontaneous reaction. So, vice versa, if there would have been a positive delta G, which is non-spontaneous reaction, you would have got a negative voltage. Okay. So, keep this in mind, and we have already talked about the concept of anode and cathode, where we told you that anode is the one where the basically electrode the oxidation occurs, and cathode is the one where the reduction occurs. Okay. So, in this case, in that situation, this is your cathode and this is your anode, because this is where the oxidation is happening, AO, and Cr, which is cathode, the reduction to remember, CrAO. AO is anode where the oxidation is happening, and cathode where the reduction is happening. Okay. Now, from here we will move on to a situation which is slightly complicated than this, and that was the whole reason to invest another class on it. Now, a situation where we will be talking about another cell. Now, let me draw the cell and that will clarify everything. So, here you have the voltmeter sitting and you have a cadmium electrode, again a cadmium electrode, but this time I have a silver electrode, no more AgCl, I have a silver electrode sitting here. Okay. So, here is a positive, here is a negative, as we have earlier showed, and now I am putting 2 different electrolyte into that CdNO3, which is aqueous, and CD is again this is aqueous, which is plus NO3 minus, CD2 plus 3 minus, whereas the other electrolyte I am mixing is AgNO3, Ag aqueous, Ag positive plus NO3 minus, which is also aqueous. So, I am now having two electrolytes which are mixed together. In this situation contain CdNO3 2, AgNO3. Okay. These are the two solutions, the solution contain these, or in other words, these are the electrolytes. So, I am not putting, now here is a situation, if you remember, when I started the class I told you I could have three situations. One situation where I have a barrier, as I have discussed in the previous class, where you have the copper and the zinc electrode separated by a barrier. Second situation is that I do not have a barrier, which I just now explained before earlier than this. Okay. We have cadmium and AgCl electrode in cadmium chloride. Okay. Now, third situation I am talking about, I have two different electrolytes and I am mixing them together. Two different electrolytes are cadmium nitrate and AgNO3, silver nitrate, and my electrode are cadmium and silver. Now, what will happen in this situation? Now, this is a very tricky situation. So, this is a situation, what I am going to now discuss is the resultant for this. So, let us write down the reaction first, because in order to understand all these things you have to write down the reaction. At the cathode, where the reduction is happening, where basically 2 Ag plus aqueous plus 2 electrons will make 2 Ag solid. Okay. Whereas, at anode what is going to happen is cadmium solid, cadmium 2 plus goes to the aqueous plus 2 electron, and the net reaction what is happening is cadmium solid plus 2 Ag plus aqueous, so once again so aqueous CD2 plus aqueous plus 2 Ag solid. So, this is the overall reaction which is happening, and in this reaction what will happen, the net reaction is spontaneous, the net reaction is spontaneous, but little current will flows through the circuit, because Ag2 plus is not forced to be reduced at silver electrode. Aqueous Ag plus can react directly to the cadmium solid surface, giving same net reaction with no flow of electrons, this is E stand for electrons, through external circuit. This is a classic situation where, if you think of it, this Ag which is coming out from here as Ag plus can directly react on the cadmium surface, and that is exactly what I was trying to highlight here. If you look at it, aqueous Ag plus can directly react to the cadmium solid surface, giving the same net reaction with no net flow of electron through the external circuit. So, essentially this is where the catch is. The cell that will not work, a solution containing two different electrolytes, it is not going to work, and this basic fundamental is needed to be understood, because once we understand this, then we will move on to our next class. We will talk about the why we needed the salt bridge and what is the role of salt bridge. So, what I will do, I will close in here, and in the next class we will be exceeding a little bit further. In the next class we will talk about a situation of salt bridge, why salt bridge is needed, why in the first case, if you remember the previous class when I introduced a semi-permeable membrane, why the semi-permeable membrane has to be introduced, what was the need for that semi-permeable membrane. So, okay, we will talk about that semi-permeable membrane in the next class. That will kind of give you the feel of a situation where a galvanic cell can work with a single electrolyte, but if you mix two different electrolytes, what will happen, and if you separate both of them, how you can force the electron to move into the circuit instead of a close-in contact which prevents it to do any meaningful work. Thank you.